Okay, I'm going to talk about this object. I hasten to impress. This is an artist's impression of what it looks like. And this is something that we observed very fleetingly through about 1 week in October 2017 in much detail. And this was actually very frustrating because even though it was a very quick encounter, it was also incredibly exciting because it revealed this object to be one of the strangest things within our solar system. Well, one of the strangest things we've seen in space altogether. And in particular, this is, as I'm going to argue, the first interstellar object that's made its way through the core of our solar system that we've identified. And that raises a whole host of questions. How do we know it's from elsewhere? Where did it perhaps come from? How did it get here? And what does that tell us about the galaxy out beyond our solar system? So it was discovered on the 19th of October in 2017 by this telescope. This is called Pan-STARRS, and it's on the island of Hawaii. Well, one of the islands in Hawaii. And just in case you don't realise, here you're looking across the clouds to the top of the big island in Hawaii. You're just seeing the tips where the mountains come up above the clouds. And this is a robotic telescope. It scans the sky every night, and the data get analysed in the morning. And it's a whole system that it looks for anything that's changing in the sky from one night to the next. And the primary objective of this is to look for dark asteroids, objects which could creep up on Earth and be potentially an impact hazard if they coincide with Earth's orbit when Earth happens to be there. And this new object was discovered because of its rapid motion relative to the background of stars. So they detected overnight when the computer scanned the data that were taken the previous night. And because it was so unusual, moving so fast, there was rapid follow-up by telescopes around the globe. And by follow-up, I just mean that instead of using survey telescopes followed the object through the sky. Now this is an example of such an image of the object, and it's helpfully outlined by a circle. If only observing by that simple, there's a big arrow saying this is what you want to look at, the sky. And the reason that the background stars are lined is because the telescope is moving at the speed of the object and tracking it across the sky to get plenty of light from it. And when it was discovered, it was already 33 million kilometres away from the Earth. So that's about 85 times the distance from the Earth to the Moon. And it's so far away that this is about as good an image you're going to get of it. It just appears as a tiny point of light. And that's why most of my talks are going to have to rely, I'm afraid, on artists' impressions of what we think the object looked like. And it came in, they tracked its orbit from when it was first discovered, and then, as far as they could before it got really faint. And they could backtrack the orbit and get pre-discovery images from the survey telescope, so they could see where it was the previous week, the previous couple of weeks or so. I think up to about 40 days or so beforehand. So you can determine its orbit through the solar system. And the first thing to notice is, the sun, in fact, let me show you. The sun sits at the centre of the solar system, the planets go around, okay? This is sped up, of course, I can't go around that fast. And the new asteroid comes in at an angle and sweeps down past the sun and then heads on out. Now this kind of trajectory, not going round the sun smoothly, like the planets, like a lot of the comets and the asteroids we already know about, strongly resembles something coming in from the outer edge of the solar system. The only things we see in orbits like this, we call it hyperbolic orbit, are cometary nuclei. So these are lumps of ice that come in from the Oort cloud. And the Oort cloud is this enormous shell. If our sun is there, surrounded by the planets and the asteroids and everything up to Neptune and the asteroid belt out beyond Neptune, about 30 to 50,000 times the distance from the Earth to the sun is a big spherical cloud of icy nuclei. That more or less marks the edge of the solar system. And any comets, out there, they're so loosely attached to the sun, because they're a long way from the gravity, a passing star can just kind of jostle things in. And those comets fall in towards the centre of the solar system. Usually they crash straight into the sun. And some are on those orbits that they go right in and then out again. And they can take, thousands to, hundreds to millions of years to fall in from the Oort cloud and then head on out past the sun. So it came in an orbit exactly like one of those comets. And when you discover a new object, you give it a telephone number, or you give it a catalogue name. So this just means if it begins with a C, this just gives you something about the date it was discovered. C just means it's a comet. However, very rapidly, it was shown not to show cometary activity. I'll come into that later, but it didn't resemble a comet. And so it was subsequently and quite quickly reclassified as an asteroid. So a comet is a lump of ice where the ice kind of boils off and gives that cloud around it and a wonderful tail. An asteroid is a lump of rock, maybe icy rock or rocky metal, and it showed that kind of behaviour. But very quickly, the speed and the orbit showed that it was moving, well, it must have originated from outside our solar system. The first such object we'd ever detected. And the International Astronomical Union, who decides names for all objects, all these catalogue numbers, didn't have any classification for things that are coming through, from outside the solar system. So it's one of a new category, I, first interstellar object coming into our solar system. It was briefly nicknamed Rama. For any of you who may remember the 1973 book by Arthur C. Clarke, Rendezvous with Rama, where this alien spacecraft comes in through the core of the solar system. But in the end, they consulted, because it was discovered from a telescope in Hawaii, they consulted with local cultural experts and linguists from the Hawaiian, and it got a new name, which is this interesting name. You pronounce it Oumuamua. Okay? You'll have to practice that later. And just to say, this apostrophe, well, it's not really an apostrophe, this is actually a proper sound in the Hawaiian language, which is more like, not quite a throat clearance or a glottal stop. So I'm probably saying woefully wrong, but Oumuamua is about as close as I can get. So Oumuamua is its name, first interstellar object. So it comes from above the plane of orbit, plunged down inside the orbit of Mercury, swung past the Sun, and then headed back out again. So if you follow the dates, it's coming out like this. At the point it was discovered, on the 19th of October, it was already out here. It had already gone past close to the Sun. And currently, it's out beyond the orbit of Saturn, it's heading out again, and not quite at the orbit of Uranus. And it won't be coming back. This is a one-time only plunge through the core of our solar system. And the closest approach to Earth was on the 14th of October, so just before, somewhere around here. And we only discovered it because it happened to come fairly close to Earth. Now, we've been following its orbit. As I said, now it came from somewhere in the direction of the bright star Vega. It's gone through and it's now heading out towards the constellation of Pegasus. Now, there are several surprising results from looking at its motion. First of all, it seems to have undergone a sort of boost in its velocity since it left the solar system, or as it's leaving the solar system. So it sort of comes in, sweeps around the Sun, and then as it's gone out, now you'd expect some slowing because it's moving away from the gravity of the Sun. The Sun's we know kind of how the Sun's gravity affects an asteroid plunging past it. But this got a bit of an acceleration, it got a kick. And so, by now, the observed trajectory is slightly further than it should be if it was just accounting for the gravity of the Sun alone. It's not a large effect, but it's still insignificant, and we don't know why it's there. That means, it's still being affected by the gravity of the Sun, but just not as much as we'd expect. Now, this kind of boost is something we expect from comets. When comets sweep down past the Sun, we observe this. And it's because a comet is a lump of ice. It may be 5, 10, 20 kilometres across, but it's still a lump of ice. And if you heat up a lump of ice, it evaporates. It goes straight to out in space. It doesn't bother with the liquid state, it just evaporates off. And when we have flown past cometary nuclei, the gases, so the water, carbon monoxide, ammonia, carbon dioxide, all the ices evaporate off in the form of jets. These are just comets we have known and rendezvoused with. And this material, as I say, is ejected in the form of small jets, and these provide a little bit of thrust And so comets often experience that just acceleration as they go past the sun. But it doesn't work for Oumuamua. First of all, the point at which this acceleration begins to kick in is not at the closest point of the sun. And with comets, when these gases come off, this is what grows their beautiful, long, thin tails. And you can detect this cloud of icy, volatile molecules that have come off the comet. And we have looked at Oumuamua, the artist's impression. Here we are. We have looked with a Spitzer Space Telescope for any of these gases being given off Oumuamua, and it detects none. It works in the infrared, which is sensitive to these kind of molecules. Molecules of carbon monoxide, carbon dioxide, what have you. There's no sign of any of them. So it's not giving off gases in the same way. It's not displaying that cometary activity, unless it's just outgassing pure water ice. And in most solar systems, you don't just get sort of water ice without any of the carbon-based ices as well, so that would be unusual. And also, okay, so it's not giving off these, it's not going through this outgassing phase. And if there is ice on this, within this thing, it's got to be buried at least a half a metre down under the surface. So it's not got gas on the surface. And as I say, it's not outgassing, when it's closest to the sun in its orbit. It kicks in after that point. And there's another objection about it not showing cometary. It's not doing this giving off material in a bit. We can't image its size. We can't take it just looks like a dot in all the images. Because the other thing, it's traveling so fast that it dims, by a factor of 100 in only a week. So it's getting dimmer very quickly. It's moving away from us very quickly. It's difficult to observe. We could observe its colour. What you can say is that it's red. This is just a plot of colours of things in our solar systems. We just do relative colours. So something's blue, it's up this end, redder, bluer. So this is just a spread of asteroids, objects in our solar system that might resemble Oumuamua. And you can see it's this red star, it's down towards the red end. And quite a lot of things are red in our solar system. Some of the, one or two of the moons around Saturn. Pluto, it's got this fabulous red sort of mass over its surface. This is due to a deposit called tholins that come from the UV sunlight breaking parts of the methane in the atmosphere that then sort of drizzle down and produce this sort of coating on the surface. Things that are exposed to a lot of radiation from the sun, it attacks the rock and it produces this red colour. We see it in Pluto. Here's the latest image of Ultima Thule, which is an object out beyond Pluto. The same spacecraft flew past it. It also shows this red colour. So the red colour is not unusual. Okay, it shows you that perhaps it's been exposed to radiation for millions of years. And if it's compared to objects in the outside of our solar system, maybe it's kind of quite rich in organic materials. It doesn't show us any features, if you analyse the light in terms of spectrum, it doesn't give us any feature of any particular chemicals on its surface. All we've got is this general colour. So we can't image it to get the shape, but what we do notice is that if you observe it for long enough, the brightness varies. This is what's known as a light curve. You have the amount of brightness the object's giving off with time. And the brightness is just how much sunlight it's directing back towards us. And this is just 1 week of observations in October. And it's got this regular variation where the brightness varies by up to about a factor of 10 every 8 hours. What this means is that the object is rotating. It also means it's not a nice spherical kind of the same shape all around, because then it would always present the same kind of area towards us, always reflect the same amount of light towards us. The fact it's got this extreme variation is due to it being a very uneven shaped object. So sometimes you only see a small part of it, sometimes you see a large part of it. So here's just one of the models that could analyse or could match this light curve. The dots are the data, the dashed line is one of the models. And here's one example where it supposes Oumuamua is a very long cylindrical object, and it's not rotating normally. It's a very irregular motion. which isn't entirely covered in this, this particular diagram. And imagine this is Oumuamua. It's rotating like this around an axis, but it's also rolling around like that and pitching like that. So it's doing a huge amount of motions, very energetic kinds of rotation. And you know, another reason why we know it's not outgassing material is because this brightness variation stays constant all through the point that it goes through that accelerated radiation. And if you go back to little rocket, you know, jets of stuff behaving like rockets on the surface of a comet as it outgasses, the thrust they provide would not only speed the thing up in its motion, but they would upset the rotation, they would unsettle it, and it would spin up the object. And because it's kept this constant spin, it's not jetting off material. So again, another argument, it's not cometary material because it's not, you know, producing that change in rotation period. So going back to models that explain the variation, well, as I say, it depends how much area is presented to you, to how much light it reflects, and how bright it is. There are, you know, you can tell something about the size, and there are a couple of models that work. One is this cylindrical shape, where you've got something that is 5 to 10 times longer than it is wide. There's nothing like that in our solar system. That is extreme elongation compared to anything we know about in our solar system. Or the other model that works is actually more if it's like a flattened pancake. Again, unique compared to anything we've got in our solar system. So whatever it is, it's a weird shape. If we want to know how big it is, well, part of doing the modelling and the size depends on how shiny it is, how much light it reflects. If you have a very dark object with a large area, that reflects a certain amount of light compared to a small object that's much shinier. So in analysing this light curve, you need to guess how shiny the object is. Now, things in our solar system, like comets, like asteroids, are not shiny. The extreme end, they reflect about 20% of the light that they receive. You know, your bog standard comet is probably about as refractive as a lump of charcoal. It's not particularly shiny. So again, how much light you receive depends on how much the light it's reflecting. So the size of the object depends on how shiny it is. If you take, well, it's also an issue that when Spitzer looked at it, they got a temperature of the object, or because Spitzer Space Telescope measures infrared, which is a manifestation of temperature of an object. The fact you didn't detect it gives an upper limit to the temperature, and if something is cold, it's not absorbing the solar energy, it's reflecting a lot of it. So that gives us an idea about the reflectivity of the object to begin with. So if it is extreme compared to anything in our solar system, or any lumps of rock in our solar system, and reflects, say, 20% of the light falling on it, it could mean it's about 200 meters long by about 30 meters wide. That gives you, so it's not big. So that's the sort of size of it. If you have a really extreme reflectance, very, very shiny, you can shrink that down to about 20 meters. So it could be a pancake 20 meters across and very thin indeed, and very, very shiny. So there is obviously some variation on these estimates, but it's, the upper limit is well under a kilometre for the longest dimension. So all these observations have told us is that Oumuamua, well, it's small, it's not a big thing, it's red in colour, which is okay, a lot of things are red in our solar system. It's probably very, very shiny, okay? And it's a very, whether it's a pancake or a cigar shape, it's still very unusual compared to anything in our solar system. It's not an icy asteroid, it's not a comet, because it's not giving off this sort of volatile material. So probably it's made of something high density, rocky material, perhaps with some metal mixed in. And the significant thing about its speed through our solar system, it's travelling too fast to have originated in our solar system. Anything within our solar system typically moves at, say, like 20 kilometres per second. This is whizzing through. The relative speed between it and the sun is too fast for it to have come from our solar system. I'll come back to that in a minute. So because it's a rocky object, the only place we produce rocky objects that we know of are in planetary systems. So we think it's from another planetary system. Basically, well, it's not from around here. It's not from our solar system. Okay, so how do you get an object from another planetary system to fall into ours? Well, a number of ways. We can have stuff torn off from the very edges of our solar system all the time. Remember I showed you, there's the planet, this is the Kuiper belt. This is like an asteroid belt out beyond Neptune. You've got the Oort cloud of comets. Now, objects out here, they're far away from the sun. They're very loosely tied to their host star's gravity. They can be easily dislodged with just like you need about 1 kilometers per second to dislodge it from the gravity of its own sun, detach it. So again, just artist's impression, but at any point within a solar, planetary system history, it's very easy to tear bits from far away from the sun, right at the edge of the solar system. We could expect that to be happening all the time from our solar system, from other planetary systems. It doesn't require much effort. Or it could be ejected at a very particular time in a planetary system's history when it's still being formed. Planetary systems form from the same a cloud of gas and dust that their host star forms from. You have the cloud, it collapses under gravity, forms the star in the centre, and the surrounding material collapses down and forms planets. And maybe, again, artist's impression, an early version of a planetary system looks like this. Within the disk, you have large planets forming. And planetary formation is quite a violent process. Big Jupiter-sized planets migrate through the disk they're forming in. They interact gravitationally with other planets that are trying to build up. And if that gravitational interaction gives it lots of energy, you just throw them out of the solar system. So this is something you need more energy to remove it from closer to the sun. It's going to be a much more violent interaction, and it only happens through the early stage of the early solar system. So this is a very particular time. So it doesn't happen so often as pulling stuff from the outside. Or perhaps it's when the host star reaches the end of its life. It blows up as a nova or a supernova, and it shreds its surrounding planets, and some of those shreds are then travelling towards us. And it happens through the death throes of the star. And the thing is, we have known that this probably happens. We can look at our solar system, we can guess how often this happens through the universe, and try and see how likely it is we'll have seen something like Oumuamua. And estimates of how many of these interstellar asteroids there are, again, lots of assumptions, but basically we don't predict anywhere near enough to account for having had one go right through the centre of our solar system. It means, it's a surprise that we've detected one at all. If you say these are being torn up from planetary systems all the time, to account for one of these going right through what is effectively a tiny bit of space, the core of our solar system, means there's got to be lots more out there. And by somewhere between 100 to 10 to the 8 times as many as previous estimates. So there's something we don't understand about planetary system formation. So there has to be a much larger population of these rogue interstellar asteroids than we had expected from all our previous calculations. Either that, and the rate of tearing things off would mean to account for the population that could account for our detecting Oumuamua, means that you're ripping off far more mass from systems than they've got in the first place. So something doesn't work. Either that or our own solar system is not a good basis for understanding what other planetary systems or systems like the origin of Oumuamua look like. So maybe they originate from systems very unlike our own. So it's coming from a planetary system from one of these mechanisms. The question is where from? I said it's coming from the direction of Vega. If it came from Vega, I forget how many light years away, it's probably something like 9.5 light years away, it would have taken it tens of thousands of years, if not longer, to come from there. And in that time scale, all the stars will have moved. We've got no way of knowing its origin. One thing very strange about its motion, though, I say it's travelling fast relative to the sun. Well, actually, it's that the sun is travelling fast relative to it. A very strange thing about this system is it's travelling at what we call the local standard of rest. Imagine this is our galaxy, we live in a spiral arm like that here, and the whole thing is turning round. Now, within that general motion, stars themselves, they get pulled on by gravity by each other, and they're going this way and that way and that way. The whole local vicinity is moving around. They've got all these local motions. And you can work out the local standard of rest by just averaging up all the neighbourhood stars in the vicinity of the sun and finding, so you average out all the motions like that or like that, and you're just left with the net rotation. That's called the local standard of rest. I'm trying to think of a good analogy. The best one I could come up with is, think if you're trying to measure currents on the ocean, you can't measure the flow in the ocean, but you can look at the boats crisscrossing it. If you take out all their random motions, you're left with the underlying current motion. Not quite sure that analogy works, but I'll go with it for a minute. But you get the idea, it's the underlying pattern of behaviour. And the sun is moving at 20 kilometres per second relative to this local standard of rest. The strange thing about Oumuamua is it's moving exactly at the speed of the local standard of rest. So it's moving fast relative to us, not because it's fallen into the solar system as much, but it's more like the solar system has run it over. Think of it as like a buoy sitting on that ocean, and where the sun is just a boat that's just sort of crashed into it and then carried on. And this dynamical motion is also problematic because when you average over all the stars, very few stars are travelling exactly at the local standard of rest, which makes its origin from round here even more unusual. Okay, so it's unlikely to have come from nearby. For all we know, it could have been torn off from a parent solar system millions, if not billions, of years ago. Maybe it's gone right through the galaxy. Maybe it's plunged already through several other solar systems. We don't know. Vega's 25 light years away, so it's taken it about 600,000 years to get here. And we don't even know it's come from Vega, that's just a general direction. So we can't pinpoint its origin other than it's not here. So obviously when you get a very interesting odd object, such as this, it does cause speculation. And one of the reasons you may have heard about Oumuamua last year in particular, is that there was a very neat little exploration of the idea from no less than the chair of astronomy at Harvard, where he said, actually you could explain all these properties if it was an interstellar vehicle, or interstellar probe, an artificial object. Now, he's not seriously suggesting it is, he's just doing this as a thought experiment, but it does explain things. You can guess over the fact that, this chance that we've got one of these travelling at random through the core of our solar system because, well, it's not that there are so many more of them that we realise, but maybe this is an artificial probe that targets travelling through the core of the solar system, stars like our own. Maybe it's targeting habitable type stars. And that greatly reduces the statistics of us having seen it. Maybe, another extreme is that the pancake-like shape, well actually if you squeeze it down and make it thinner and thinner, maybe it's like a solar sail. Okay? Maybe you've got a very, millimetre thick, 20 metre across, very shiny solar sail, and it gives that extra acceleration from radiation, the pressure of light as it goes past the sun, and that just pushes it as it goes on out of the solar system. I will say it's not clear how a solar sail could tumble in the way that we observe this. But it's just an interesting exercise. Nobody really thinks it's an artificial object, but they did check it with a range of radio frequencies and failed to detect the object at any radius. So it's not giving off, it's completely silent, it's not giving off any radio signals. So what can we do to learn more about the subject? Well, not much as far as Oumuamua is concerned. It's travelling so fast. It is so dim that we can't really observe it anymore. We couldn't catch up with it with a spacecraft. It would be by the time the spacecraft caught up, it would be very difficult to rendezvous with it. So we can't examine this in much more detail. What we can do is we know these exist. We can look for others. We're going to have targeted searches for others. Now this is difficult to do because we only came across this one by random in a survey telescope. And we've had survey telescopes for a number of years and this is the first one we've turned up. Well, things are changing. There's a new generation of telescopes. In particular, there's for example, the LSST, which is the Large Synoptic Survey Telescope, which is being built. And when it becomes, operational, is going to be far more sensitive to objects like Oumuamua, not just going close to the Earth, but perhaps going through the outer parts of our solar system. As soon as we discover the second and the third, we can begin to look at those statistics, we can look at the properties of these objects, and we can find out more about their origin, and perhaps, you know, ultimately, that will give it, so it's just a drawing of the LSST telescope. So we can hope within its first year of origin, which is due the early 2020s, we will be discovering many, many more of these interstellar objects, and we'll learn much more about where they could come from. We'll learn about where are they born. Are they born in planetary systems that are very similar to our own solar system, or that they are very different? So how, when in a planetary formation, you know, is it in the formation of the planets, or is it from the outside of the system, or in the death throes of the stars? When do they come from? How do they get loose? It gives us a clue about what happens as planets form, other planetary systems, the contents of other planetary systems, and maybe if we can catch one, we'll see one coming in, and we can perhaps rendezvous with it. We can see one enough far away, perhaps the next, if not the next, then somewhere in the next few, we'll be able to send a spacecraft out to actually rendezvous with it and find out. So that is my end point. I just realised one thing I didn't tell you is Oumuamua, if you translate it from the Hawaiian, it roughly means messenger or scout coming from the distant past. So which I think is a very nice poetic thing, because it's reminding us that this, if you consider it a messenger or scout from outside of our solar system, and potentially, when telling us how planets form, the planetary systems work around other stars, is telling something about our own solar system, perhaps the history of our own solar system. And the nicest thing of all, it means that perhaps our solar system is not as isolated as we had already thought. Thank you very much.